Hello friends, I'm MV Deshmukh. Today's article is the Gram-Schmidt process. So this is the second video regarding the Gram-Schmidt process. In the earlier video, we saw how we can use the Gram-Schmidt process to convert the any basis set into orthonormal basis set. So what is the use of this? We write here again. Use. Suppose let V be an Euclidean inner product space, If V be the Euclidean inner product space, suppose V be the finite dimensional, therefore V has basis set, and any basis set is converted into orthonormal basis set by using Gram-Schmidt process. So this is very powerful method to convert the any basis set into an orthonormal basis set by applying the step-by-step procedure. So in this video we consider the example on three-dimensional vector space. That is, we consider let R raised to 3 be an Euclidean inner product space, and some basis set is given to you, and to convert the basis set into an orthonormal basis set. Let us consider the examples. Let R raised to 3 be an Euclidean inner product space. Use Gram-Schmidt process to convert basis set. Suppose consider the basis set is U1 bar, U2 bar, U3 bar. This is the basis set containing these three vectors, because R raised to 3 is a three-dimensional vector space. The basis of R raised to 3 contains the three vector, and we want to convert the basis set into an orthonormal basis set. So we use to convert the basis set into an orthonormal basis set using Gram-Schmidt process, where the three vectors are given, where U1 bar equal to 1, 1, 1, the vector U2 bar equal to -1, 1, 0, the vector U3 bar is 1 to 1. Now we use this step-by-step procedure. Step 1. Let us define the vector V1 bar is as U1 bar. That is, first consider the vector U1 bar. Call this vector U1 bar as a V1 bar. This is the first step. Initially, the first vector you treat as a new vector V1 bar. Step number 2. Let us consider the vector U2 bar. The new vector which is obtained, we denote by V2 bar, is U2 bar vector minus its projection of U2 bar vector on W. Means what? Suppose this vector is u2 bar and suppose w is the subspace. The projection of u2 bar is on here, so this is the projection of u2 bar vector on w. W is the subspace and this subspace spanned by the previous orthogonal vector v1 bar. The vector which is perpendicular to that we call as a v2 bar. Therefore, the value of v2 bar is u2 bar minus projection of u2 on w. So u2 minus projection of u2 bar on w. So v2 bar equal to u2 bar minus. So we can calculate the projection of u2 on w. W is spanned by one orthogonal vector v1 bar. Therefore, projection is obtained as u2 bar v1 bar divided by norm of v1 bar square into v1 bar. So first we can calculate the inner product u2 bar v1 bar, then norm v1, we substitute the value, after calculation we get the v2 bar. So we call this equation is 1. First we can calculate u2 v1. So here u2 is given, u2 bar vector is here minus 1 1 0 and v1 bar is already given here 1 1 1. We find out the inner product, and that inner product is Euclidean inner product because already the vector space is Euclidean inner product space. So inner product of u2 v1 is just minus 1 into 1 is minus 1 plus 1 into 1 is 1 plus 0 multiplied by 1 is 0, which is equal to 0. So inner product of u2 v1 is equal to 0. So this numerator is 0 here. So whole term is 0. Therefore equation v1 is convert as v2 bar is equal to u2 bar minus this one is 0. So we get only the u2 bar vector. So v2 bar is nothing but the u2 bar vector and u2 bar is nothing but the minus 1 1 0. So this one is the second vector we calculated here. This one is the first v1 bar. So at the end of the step number 2 we can calculate the second orthogonal vector v2. Now we go to the third v3 bar. Step number 3. In the step number 3 we have to calculate the v3 bar vector. V3 is calculated by using the third vector u3 bar minus its projection of u3 on w. So where is the projection? So let us see here. Suppose this vector is u3 bar in the three-dimensional space. Suppose this is a subspace w which is spanned by the orthogonal vector v1 bar v2 bar, which is already calculated in the step number 1 and 2. The subspace w is spanned by v1 and v2. So the projection of u3 on w is, suppose this is the projection vector of u3. So this vector is orthogonal, we call it as v3. So v3 is equal to u3 vector minus its projection. So u3 minus projection of u3 on w, but remember w is spanned by v1 and v2. So this projection is obtained here by using the formula v3 is equal to u3 bar minus projection is u3 bar vector, previous orthogonal vector is v1 bar divided by norm of v1 bar square into v1 bar minus inner product u3 v2 divided by norm of v2 square into v2 bar. So we call is equation number 2. So to compute the v3 bar vector, it is enough to first calculate inner product u3 v1 first, then it's norm v1 bar, u3 v2 and norm v2 bar. Once you find out these four quantities here, put here, after calculation we get v3. So let us one by one we calculate u3 v1 first. So we have a vector u3 bar is equal to, u3 bar is given in the example, u3 bar is 1 to 1, so we can consider this, u3 bar is 1 to 1, and v1 bar is already we calculated in the step number 1, v1 bar is 1 1 1 1 1 1. Now we can calculate inner product u3 v1. So this is Euclidean inner product component wise multiplication. 1 into 1 is 1, plus 2 multiplied by 1 is 2, plus 1 is multiplied by 1 is 1, so addition is 4. So we get inner product u3 v1. Now we find out the norm of v1 square. So norm of v1 bar square is nothing but the inner product of v1 bar is equal to, so v1 bar is already here, so we can calculate the inner product of v1 is, so v1 is multiplied to v1, that is 1 square, plus 1 multiplied by 1 is 1 square, plus 1 multiplied by 1 is 1 square, so this one is 3. So we get inner product u3 v1 norm of v1 square. Now let us find inner product of u3 and v2. So we have a u3 vector, so we need v2 bar vector here. v2 bar is calculated at the end of the second step. v2 bar is equal to minus 1 1 0, minus 1 1 0. Now we calculate inner product u3 v2, inner product u3 bar v2 equal to, inner product u3 v2. So Euclidean inner product, the first component is 1 multiplied to the first component minus 1, that is 1 into minus 1 is minus 1, plus product of second component 2 into 1 is 2, plus the product of third component 1 into 0 is 0, the answer is 1. So this is the inner product u3 v2. Now we have to find out the norm of v2 square, that is inner product v2 bar, that is v2 is multiplied to itself v2, so minus 1 into minus 1, so this is minus 1 square, plus 1 is multiplied to the 1, so we get 1 square, plus 0 is multiplied by 0, so we get a 0 square, so addition is 2. So in this way we find inner product u3 v1 norm v1 square, inner product u3 v2 is 1, norm of v2 square is 2. Now we put all these four values in the equation number 2, and we have equation number 2 here. See, this is the equation number 2. So we start here, v3 bar is equal to u3 bar vector minus inner product of u3 v1, we already calculated, inner product u3 v1 is 4, so we write the 4, divided by norm v1 square, so norm v1 square is 3, that is divided by 3, and this vector v1 bar, so we keep this vector v1 bar here, minus inner product u3 v2, already we calculated here, inner product u3 v2 is 1, so 1 divided by norm of v2 square, so norm of v2 square is 2, and then the vector v2 bar is multiplied, we write the vector v2 bar here. Okay, so in this way we substitute the inner product and norm here, we have to simplify this step. equal to inner product u3 is already given. Vector u3 is 1 to 1. We have to substitute this value 1 to 1 minus 4 by 3. v1 bar, we have a vector 1 1 1 minus 1 by 2. v2 bar, we have a vector minus 1 1 0 minus 1 1 0. This is a simple arithmetic calculation. So we take the first component of each vector. So the first component is 1. In the second vector, so 4 by 3 is multiplied here, so 4 by 3 with negative. In the third vector, the first component is 1 by 2 is multiplied by minus 1, so minus half, but minus minus plus, so plus half is here. Now we take the second component 2. Its second component here 4 by 3 into 1 is 4 by 3 with negative sign, so minus 4 by 3. In the third vector, the second component is 1 but multiplied by minus half, so minus half. Now the third component is here 1, so we write the 1 minus 4 by 3 times 1, so minus 4 by 3, and here minus half times 0 is minus 0. After simplification, simple arithmetic calculation, so 3 into 1 is 3 minus 4, so minus 1 by 3 plus half. 3 2 6 minus 4, 2 by 3, this is minus half. 3 1 3 minus 4, so minus 1 by 3 is here. So after addition of these fractions, so 2 1 minus 2 plus 3, that is 1 by 6. This is 4 minus 3, that is 1 by 6 again here, and here minus 1 by 3. So we get the third vector v3 bar here. So in this way, we have a vector v1 bar here, v2 bar, and we have a vector v3 bar. So we get the orthogonal vector. So we write separately here. So we have the set v1 bar, v2 bar, and v3 bar. So v1 bar is here 1 1 1, v2 bar is minus 1 1 0, and v3 bar vector is 1 by 6 1 by 6 minus 1 by 6. This is the orthogonal set. Orthogonal set. And we have a very nice theorem that if the set is a non-zero, that contains a non-zero vector, and if it is an orthogonal set, then that set is a basis. So this is the orthogonal basis. Now we want to convert the basis into orthonormal basis. So we have to normalize this vector. So the first vector v1 bar, we normalize it. Now normalize each vector. Normalize each vector. And the procedure is to normalize each vector means every vector divided by its norm. So the first vector v1 bar divided by its norm v1 bar. So we get the new vector w1 bar here. So v1 bar is the vector, so 1 1 1. Norm of v1 means it is the square root of inner product v1 bar. So which is equal to 1 1 1. Inner product of v1. So here this vector is multiplied by itself. So 1 into 1, 1 square, 1 square, 1 square. So this number is 1 1 1 divided by root 3. So we get the w1 bar vector is 1 by root 3, 1 by root 3, and 1 by root 3. So we get the first orthonormal. Now we consider the second vector v2 bar and normalize it. So second vector v2 bar divided by norm of v2 bar. So we call this vector is w2 bar. So v2 bar is minus 1 1 minus 1 1 0 divided by norm of V2 means it is the square root of inner product V2 bar V2 bar. So which is equal to minus 1 1 0. Inner product of V2 bar is with itself V2. So this is V2 bar. We find out the inner product of this vector to itself. So minus 1 into minus 1. So this is minus 1 square plus 1 into 1 is 1 square plus 0 square. On calculation, so the answer is in the denominator is root 2. So hence we get the W2 bar vector is minus 1 by root 2, 1 by root 2 and 0. So we have a second vector W2 bar. Similarly, we have to find out with W3 bar, that is we have to normalize this vector W3. This is a V3 bar vector. We have to normalize it. So the third vector V3 bar, we want to normalize means divide this V3 bar as a norm of V3. We call this new vector is W3 bar. V3 bar means 1 by 6, 1 by 6 minus 1 by 3. 1 by 6, 1 by 6 minus 1 by 3 divided by its norm of V3. So it is the square root of inner product V3 into V3. So here we calculate the inner product of V3 and V3. So this is a V3 bar vector. We find out the inner product of this V3 is V3. That is 1 by 6 into 1 by 6 is 1 by 6 square plus 1 by 6 into 1 by 6 is 1 by 6 square plus minus 1 by 3 into minus 1 by 3 minus 1 by 3. So we find out the inner product of V3 with V3 bar vector in this way. So this one is 1 by 36, this is 1 by 36 plus this is 1 by 9. So LCM of this is 36. So here we multiply by 4, here multiply by 4. So the numerator is 4, 5, 6 upon 36. So we put this value here, which is equal to 1 by 6, 1 by 6 and minus 1 by 3 divided by square root of inner product V3B. V3 we already calculated. This one is 6 by 36 here in this way. After simplification of this, W3 bar is equal to, so numerator is 1 by 6, 1 by 6 minus 1 by 3 divided by, this is root 6 and denominator is only 6. This 6 is goes to the numerator. So this one is 6 upon root 6, 1 by 6, 1 by 6 minus 1 by 3. Multiply this number to every component of this vector. So we get that 6 cancel. So 1 by root 6. This is multiply here 6 cancel. So we get a 1 by root 6. And 6 into 1 is 6 upon 3, that is 2. So minus 2 by root 6. So we have the vector W3 bar here in this way. Hence the orthonormal basis set is W1 bar, W2 bar and W3 bar is equal to W1 bar. We have a vector W1 bar is 1 by root 3, 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 1 by root 3. Now the second vector W2 bar is minus 1 by root 2, 1 by root 2, 0, minus 1 by root 2, 1 by root 2, 0, and the third vector is here 1 by root 6, 1 by root 6 and minus 2 by root 6. So in this way we convert the basis set into orthonormal basis set by using Gram-Schmidt process. If we check these two vectors are orthogonal or not, they are orthogonal, their inner product is 0, inner product of these two vectors is 0, inner product of first and third is also 0, therefore this is orthogonal set, and norm of every vector is 1, therefore this set is orthonormal basis. So in this way we use the step-by-step procedure to find out the to convert the any basis set into orthonormal basis set. Okay, so I hope that you understand the concept how to convert the any basis into orthonormal using Gram-Schmidt. Okay, thank you very much.